Hey everybody, welcome to this first module. In this first video, I want to go over some circuit theory. So let me go ahead and share my screen here. All right, this is the lab background and procedure document. And if we go onto the Canvas page, under the first module, you can find this document under the Resources tab under Background and Procedure 1. And you're welcome to download it and follow along if you'd like. So for this first week, we're going to be looking at circuits, spice, and everything nice. I just thought that was clever. And to start things off, I usually like to go into some definitions. And this first definition, right, we start our discussion with this idea of a device. And a device has some defined electrical behavior. Some examples of devices are resistors, capacitors, voltage sources, and, well, in order to use a device in a circuit, we need to have terminals. These are points at which we connect the device into a circuit. And when we have multiple devices, we can begin to talk about a node. And so if I connect the top two terminals and the bottom two terminals, then we have a node here and a node down here at the bottom. And a node is just this junction of terminals that are all connected electrically. And then, now that we have a set of connected objects, we can define a circuit. So a circuit is just a set of connected devices. And when we're analyzing our circuits, it is helpful to define the circuit ground. So the circuit ground is where we define to be 0 volts. And this can be helpful when we begin to talk about current through devices and voltages across different devices. And so now we can define a branch. A branch is just a path between two nodes. So we have our top node up here, and there's a branch going through this leftmost device down to ground, and there's another branch through the rightmost device to ground. And that would be two examples of branches, right from this top node to the bottom node. And now that we have this idea of a branch, we can begin to talk about what it means for elements to be in parallel and what it means for elements to be in series. And for some motivation, we like to talk about elements in parallel and elements in series because it allows us to simplify a complicated mess of circuitry by kind of like defining how these objects' electrical characteristics behave when they're connected in parallel or when they're connected in series. So let's say I have these three devices. If they're all connected between the same two nodes, and right, so we have the top node here and the bottom node here, but they're each on a separate branch. These three devices are connected in parallel. But if we are on the same branch and we have these three devices, then they're connected in series. This is parallel, this is series. And so the series connection is topologically the same as if I were to draw it maybe like this, and you'll see this sometimes. So this is another series connection on the left that is topologically the same as this other one on the left that I've drawn here. Right, so this right one and the left one are the same. Uh, a little equal sign. And so now that we have these connections out of the way, we can begin to talk more about electrical characteristics. So the voltage is the amount of work required to move an electric particle. And so we're looking at circuits, we're interested in the movement of current, and this current through some device or some voltage applied across the device in turn creates current. And then when we have current and voltage, then we begin to have power, which we'll probably talk in more about in lecture, I'm assuming. Right, so we have current. It's the rate at which these electric particles are flowing. Right, so when we have an electron, the electrons are moving from low to high potential, and the current is then moving, it's those particles that are moving against the flow of these electrons. And the resistance is what is slowing these particles down, more or less, right? It's absorbing kind of the energy as the current is flowing. And now we have voltage source. It's a two-terminal device that supplies voltage, right? So it has some constant voltage and ideally zero resistance. So we don't want anything flowing through that. And then a current source is a two-terminal device that supplies current, which has infinite resistance, ideally. And a resistor is some two-terminal device that has some nominal resistance that's defined. Ohm's law and Kirchhoff's current law and Kirchhoff's voltage law. So Ohm's law is how we describe current or voltage. And so the current is this ratio, the voltage divided by resistance. We could also write V is equal to IR, and it's just a way to analyze a circuit. And Kirchhoff's laws are more or less a statement of some kind of conservation of energy. And so the current into a node has to equal the current out of the node. So if I have something like this, right? So the current coming out of this voltage source, this plus and minus in a set of a circle is a voltage source. Well, the current coming out of here has to be the same as the current going through this resistor. And so what goes in must come out. And Kirchhoff's voltage law, the voltage across a loop sums to zero. And we can think of that as what goes up must come down. What goes in comes out. And so if this is a 5-volt source, and we define this to be ground, well, we go up 5 volts, so we're at 5 here. And that means that the drop across this resistor must be 5 volts. Sorry, I drew that wrong here. So we're going down 5 volts. And some corollaries that follow, right? So voltage in parallel, all the voltage across these elements in parallel are equal. If I have a voltage source and a bunch of resistors, well, the voltage across all these resistors are the same. And if I have a current source, a couple of resistors, well, the current through elements in series is equal. So the current, say this is 1 amp, well, then the current through here is also 1 amp, the current through there is 1 amp. And if this was 1 volt, then these are all across each of these 3 resistors, also a 1 volt drop. So equivalent resistance, this is where we begin to have some ideas that allow us to simplify circuits, make it easier to analyze. Right, so if we have a set of resistors that are in series, and we just add up their resistance to get the equivalent. And if they're in parallel, we have the set of resistors that in parallel. We take the reciprocated sum of reciprocals. And just as a quick little derivation, if we have two resistors, we take 1 by R1 plus 1 by R2, and we reciprocate that, and we get 1 divided by R2, right? And then we add R1 divided by their product, it's R1, R2. And so 1 over that is going to be R1, R2 over the sum. And this can be helpful when we're condensing our circuit, and we'll go over that an example shortly. So circuit symbols. This is a symbol for a voltage source. This is a symbol for a current source. And this is a symbol for a resistor and the symbol for ground. So the voltage source, also drawn like this, is a device that has some polarity. And so if we define this to be ground, or I guess, so if this was a 5-volt source, and if this bottom node is ground, then up here is 5 volts, right? So the potential exists in this device, right? So the positive terminal is where this defined voltage increase exists. And likewise, the current source is another device that has some polarity. So current is coming out of the device through that arrow. The resistor is not does not have any polarity associated with it. We can connect the resistor any which way and it will behave the same. And a ground is just a label of a node. And so it's just where we define our circuit to be 0. So here are some examples. I'll go through these first two and let you convince yourself of this one. So the circuit with V1 has 3 nodes and 1 loop. There's this node tied to the positive side of V1, the node tied to the negative side of V1, and the node tied to the 2 resistors. The circuit with I1 has 2 nodes and 2 loops. So here's I1. There's this top node again and the bottom node. And the loops, well, so there's actually 3 loops, I guess. So there's this loop with I1 and R3. There's a loop with R3 and R4, but there's no source tied to these two, so I didn't really count it as a loop. I counted this outer loop with I1 and R4, but someone might argue that there are 3 loops in this, so we'll just go with that. And then, like I said, you can convince yourself of this one, right? R1 is in series with R2, R3 is in parallel with R4. Hopefully you can see that. And I'm going to make a separate video for the electronic test equipment because I want to go over a quick example of reducing a set of resistors here, a resistor network. So our goal usually is to determine the equivalent resistance seen by the source. And so here's our source. And sometimes it's seen by our load, but in this case, we're just looking at sources. So there's our source. I'll label this R1, R2, R3, R4, and R5. And when we have a problem like this, we want to collapse our network in towards the source. And so we can see that R4 is in parallel with in series with R5, sorry, because we can trace that they're on the same branch here, right? And you don't really have to draw it, but just so that you can kind of visualize the process here, I'm going to erase this. And so what happened is we have collapsed this to R4 plus R5. And this is now in parallel with R3. And I'll draw this again. Parallel with R3. And this mess is now in parallel with R2. So let me collapse this even further. And all of this is now in series with R1. And we can say that this is the equivalent resistance seen by the source. And I'll go ahead and simplify this further. So when we have these two objects in parallel, and we take the product of them and we divide by their sum. Put R3 here. Did I do that right? Yeah, so you take the product of the two and you divide by their sum when they're in parallel here. And if we simplify this, so now we're in parallel with R2, and this is all then in series with R1. So we take the product again, R3, and now we multiply in R2, and then we can add them all in. And this is all in series with R1. And so that would be an expression for the equivalent resistance seen by the source, where our original circuit, I think, was R2, R3, R4, and R5. And I just wanted to go through an example of that because that tends to be tricky for some people, and it will be the bulk of what we are doing for the procedure this week, right? We're going to be simplifying the networks and kind of like solving for the different voltages and currents. And I think the voltages should hopefully be pretty straightforward and the currents, but the trickiest part can be breaking down the network into something simple. Right? So then what we would have is something like this. And we have our source, and so it's got some voltage, and we can easily find the current by taking the voltage divided by their equivalent resistance, and that will determine the current that's going through R1 here, and the current that's going through this whole network. And I'll leave some of the work up to you guys, obviously, right? So we've got the exploration and procedure, exploration and experiment for lab time. So with that, I think we'll call this video. I'll see you in the next one. Thanks.